Yep. We're gonna have to do some chemistry at some point. I know. I know, but now you have to do the next stuff. Okay, so we're still kind of talking about just terminology and ideas. So physical change versus chemical change. So what you see here is a physical change. So it goes from solid carbon dioxide to gaseous carbon dioxide, which is a process known as sublimation. You remember our nice little, oh wow, that's way up there. I'm not going up there. There's a map on all of the processes, but but you notice at the end it's still carbon dioxide. It didn't change the substance. This is usually where I kick philosophy professors out of the room because they, what do you mean by substance? Out. I mean the stuff shit's made from. Okay. So you still have carbon dioxide at the end. Who can tell me what solid CO2 is? It's a lot of fun on Halloween. Solid CO2. Makes you look like you have magical powers. It does, yeah. What it does, you have to put it in liquid and then it will do dry ice. Solid CO2, dry ice. Now, what about a chemical change? Now, this is something you might want to pay attention to. This combustion equation, this is the standard form of the combustion equation. You have a compound with mixed with oxygen, it combusts, and every hydrocarbon will give you carbon dioxide and water. Those are always the products for hydrocarbons. Later on, if we work with it, if you see a metal in there, you'll get the metal oxide. Now, I just called that a hydrocarbon, though. In chemistry, what does hydro mean? Nope, it means it has hydrogen attached to it. So, but it's important to go through this terminology because you've heard words like this, but in chemistry, they always tend to mean something a little different. Now, always remember, your chances of being killed by a cow are slim, but never zero. Also, always remember as you're going through this weekend and trying to have a good time, we could be dead in 7 minutes. We wouldn't know. If the sun explodes, we won't know for 9 minutes. We're like, this is a great day. What's that? Kaboom. I always love throwing that stuff in. Kind of like I love telling people. I remember my first year, someone came in and said, I feel so good today. I've only had 1,100 calories. I'm like, no. No. See, the nutritional calorie is actually the kilocalorie. So you just had 1.1 million calories today, but that's okay. That's okay. It still works out to be the same thing, but there are people who go, no. Let's start looking at liquids. Okay, so we've been talking about intermolecular forces. So all this is going on inside of a liquid. If it's a nonpolar liquid, nonpolar solvent, so you usually just have dispersion. If it's water, you have dispersion, dipole-dipole hydrogen bond. But there's going to be forces going on inside the liquid. Molecules down in the liquid are being pulled on in every direction equally, okay? At the top, they're not. Molecules at the top are only being pulled in the directions where they touch the liquid, and then they're not, and so they have this imbalance of forces. So between the intermolecular forces themselves and this imbalance of force, all the molecules on the surface of the liquid pull together tightly to give us what we know as surface tension. And then you have the little buggies that make use of the surface tension and they can walk on the water. And that's brusque, but I actually think that their feet use electrostatic interactions. So let's start talking about what we know as capillary action. Now, I said capillary action. You notice how you have capillary attraction and capillary repulsion? Those both count as capillary action. So it just depends on what force is dominating. So I'm able to use the computer and I make this nice little structure over here. Notice how it's very irregular. That can help you in a little bit. That is a silicon dioxide. You notice the water starting to climb up the wall, the silicon dioxide. Notice those little oxygens sticking out in space. Well, then the water is going to start to form hydrogen bonds and climb the wall of that. You saw this in the lab. What is that little divot it creates in the fluid? A meniscus. So you can have a convex meniscus and a concave meniscus. Which is which? Yeah. So your concave, if you're looking from the top down, just think of it. Concave is dipping down. Convex is bubbling out. But that silicon dioxide, who can tell me what it is? It's an irregular silicon dioxide structure. You often have to melt sand to get it. Glass. So this is why you get that meniscus. The water starts climbing the walls of the container you're in. Now, you want to make sure you get the difference between adhesion and cohesion. So your adhesion is what causes your concave meniscus. When adhesion dominates, you get like the water climbing the walls of the container. Cohesion is when molecules inside the liquid themselves hold on to each other much more tightly than adhesion can pull them apart. So cohesion would be what you're seeing in the mercury. It's where you're going to get that convex meniscus. And it has to do, so again, adhesion is your fluid is going to be interacting with the container. Cohesion, the molecules of the fluid interact with each other much more strongly. I don't think that was proper grammar. Much more strongly. I don't know. I'm a math person. I don't. It was some of our biology majors that forced me to change my exams. I would write a question and then leave a space to answer it. Found out that space was too big because I started getting little novels. No, I want it short. No, have you had that yet? Your grammar is checked. You have to write like paragraphs, and have you done that yet in biology? You'll get there. No, usually Hardy has you write in like paragraphs, and Buckman will. Oh yeah, yeah. So I would put that on. I would put spaces on my test, and I'd have students fill the whole thing up. And I just went back going, no. There was a test I put TLDR on like 3 of the problems. I'm not. So remember, I'm a math person. Now let's talk about something you've probably heard of before called viscosity. So again, a fluid's resistance to flow, you can think of it as a fluid's internal friction. Now, I don't know how you'll feel next year. That's how I felt in organic chemistry, but I'm a math person. If you have a biology brain, you're going to do really well in organic. Organic is a lot of cycles, not a ton of math, but like, here's your structures. Where are your structures? Where do the electrons go? What are your cycles? So the main idea of viscosity is you have to think about how hard it is for the molecules to slide past each other. And so what we see up there in the graph, as temperature increases, the viscosity of gases increases, the viscosity of fluids decrease. Did anyone explain that? So look at the graph on the top right. You see how the viscosity of gases increases and liquids decrease as temperature increases? Did anyone explain that?
It's like material, like it's really increase of the heat on them, they make it so much more.
What are you breaking apart when you increase the heat into the fluid? Yeah, so your intermolecular forces, you're breaking them down. So you're going to have less internal friction. What about a gas? So they're going to move faster. You also get this fun little thing where you are going to start to get extra excited states along a Boltzmann distribution. I always hope someone will hear that. I really want to know what that is, and then take physical chemistry. What else can gas molecules do as you heat them up? They're not just gonna move faster, so yeah, they're gonna be smacking into each other a lot more, so they're smacking into each other more pressure. What else are they gonna be doing? What other kinds of motion will they start to gain as they do that? They're gonna be in vibration and rotation. So as the molecules heat up, they're not only moving faster, they're gaining vibrational states and rotational states. And so this again makes the molecules of the gas much more viscous. You would never guess that silicone sealant is right at the same viscosity as peanut butter. And honey's very close to mayonnaise. Let's work on one of our mock exam questions. Remember, you can talk to each other. What does ammonia have that even though nitrogen is at the very top of the column and is the smallest atom there, would spike its boiling point up? Ammonia is the only molecule that has this. Well, it will have that, but some of the others will too. So we need to find something unique to the ammonia. It's C, hydrogen bonding. Because for what does hydrogen have to be bonded to for that to occur? We gave three very specific atoms. Chlorine. So you see that the ammonia is going to bring in hydrogen bonding. Going to make its intermolecular forces a lot stronger. So even though nitrogen is the smallest atom in the column, it's going to have its boiling point spiked up due to the hydrogen bonding. Here's some more. Here's another boiling point trend. Can you answer this one? Now, those are all noble gases. And believe it or not, those are noble gas molecules. A noble gas molecule is just a single atom of the gas. And what do we say about larger atoms? Well, what can you do to them that affects the intermolecular forces? All right, what do we think? It is A.
Less stable.
No, not stable. So remember the larger atom. I guess you could say that if that's how you remember it. Remember the larger atoms, the electrons are easier to move. And so in the London dispersion forces, when I get instantaneous dipoles and then induced dipoles, the dipoles in the larger atoms are going to be much greater. And so the stronger those dipoles, the stronger the electrostatic attraction, the higher the boiling point is going to go. Now we have two questions. What is responsible for capillary action? It is E. Because remember I told you to pay attention to capillary action, which refers to both capillary repulsion and capillary attraction. So both of those count, and they're governed by these two different forces. What about the second one? It is true. Remember we talked about the uneven dispersion of forces on the surface of the fluid? The stronger those are, the tighter they're going to pull the molecules.
Like water, that
Mm-hmm. Mm-hmm.
Feel like you bled,
What?
feel like you bled, have you ever
No,
bled?
I don't want to now.
It's like a cornstarch and.
Oh, it's a non-Newtonian fluid. Yeah, so it's a fluid. You can like put your hand in it, it's fine, but then you punch it and it breaks your fist. Non-Newtonian fluids are fun.
Is that a high purpose tension? Or
No, I think it's something else that does that. It might. I'd have to look at it. I'm not real sure. I just know it's a non-Newtonian fluid. So those are definitely fun. Try these two. Look at that one. It's CH225.
it's like a wall.
What do you think that is?
Very true.
Uh-huh. It's a fat molecule. And the carbon hydrogen bond is very, very, very stable. The more of them you get, the more stable you get electron delocalization, which is why you have to work very hard to break fats down.
high viscosity, flows easier or.
So low viscosity is easier flow. High viscosity is a higher internal friction. Think of this in terms of intermolecular forces. Size of the molecule, intermolecular forces. Do we have any guesses from the back row? What would you guys do if I just went, you?
But
I don't know. I just don't like putting people on the spot.
I think. Like it's not.
So it is B. Let's talk about why. Let's talk about why. So first off, when we're looking at this, one of the first things you can compare is some of these are liquid, some are gas. Now, most of your gases are going to have quite a bit lower viscosity, especially these. These are tiny molecules. So I'm going to go that. So that one, we know that's a fat molecule. That's going to be like an oil. That's going to be pretty high. The calcium chloride. Again, we have not calcium, carbon chloride. We got to end this week. We got to end this week, boy. I'm losing it. So we'll just cancel out the liquids. I'm done talking about that. We'll go to the gases. So they're much more spaced out. They're going to get by each other easier. However, the hydrogen chloride has an extra intermolecular force in dipole-dipole interactions that the nitrogen does not have. So that's going to cause the viscosity of the hydrogen chloride to go up. And why did I call that hydrogen chloride and not hydrochloric acid? The gas, what does it have to be acid? Huh? No, you're close. You're on the right path. Would that have to be? I could bubble that into water and turn it into hydrochloric acid. What does HCl have to be to be considered the acid? Aqueous. That's the aqueous phase. What about this next one? Convex meniscus. Which of the following explains this behavior? Which one was the convex? Yep. Nope. It's B, cohesive forces. Because remember, the convex is, it has to do with the molecules inside the fluid being more strongly attracted to each other than they are to the surroundings. Adhesive, so your capillary reaction is either going to be adhesive or cohesive. If you see a standardized exam where adhesive or cohesive is not an option, then go for surface tension. That's it. That's kind of the way you would eliminate your possibilities.
Like say kind of like that. Convex, not.
Well, that's because you're at the very top and the water molecules are still being attracted to those oxygens in the glass. So now they have to come back down to reach it. All right, structures and types of solids. So here we see the difference between crystalline and amorphous. A crystalline solid has very high symmetry at long ranges. Amorphous, not so much. Irregular structures, they could be the exact same chemical compound. Amorphous has little to no long-range symmetry. So imagine these are both silicon dioxides. This exists in nature. The amorphous one on the right, what do you think it is? An irregular silicon dioxide. But that's the one on the left. That's the crystal.
Wow.
Nope, it's glass. So exact same chemical structure, different macro structures. Well, different microstructures too, but okay. So moving on, crystals. So what you see is crystals are going to are be in what's called a lattice. The lattice is going to dictate where the spot of every single ion in the crystal. Most times your crystals are ionic solids. You can have covalent crystals. Can anyone think of a crystal that has covalent bonds, which is ionic? Correct. Yeah, I didn't think of that one. Yes.
Salt.
Nope, that's ionic. What about a crystal that's only carbon? Diamond. You think that the Beers Corporation for making those popular, like in the 1800s, nobody wanted them. And there was a massive ad campaign saying, hey, you show someone this person, what? It's coal. It's compressed and heated coal. Look, you have to think about how rare something is. Coal, carbon, not that rare. If you want to show someone they're special, give them something that's actually rare, like gold. Why? See, all the gold we have is all we're ever going to have. Our planet could get more, but we don't want it. Why is that? Can anyone tell me where gold is made? Oh, that would be one of them. Ah, yes. So gold is fused at the moment of either nova or supernova of the main sequence star. It literally takes a star's death to make gold. And now there are bigger stars that can fuse it, but dramatic purposes. But the gold will be trapped in those bigger ones due to gravity. But yeah, so unless we're either going to get hit by a comet or an asteroid, or we are in the direct path of a supernova blast wave, we're not going to get any more. We don't want either one of those. Because you will not live to enjoy the gold. Now, the asteroid wave, we can go to the ground from more people. That's possible. Now, look at the chunk of sodium chloride there. Believe it or not, that's table salt. That's how it comes out of the mine. So do you notice how it looks like it has little cubes popping out of it? So the macro structure of crystals is going to mirror its unit cell. So crystals are very much like fractals. You're going to get the same structure over and over and over at larger and larger level. And I know that's funny. I don't know what a Golgi apparatus is. Nope. But I know that's funny. I don't know why some designers come up with the stuff they do. know if it's still, I don't think it's still this way. When I was in high school, someone would jump you in the parking lot for your Jordan sneakers. Like those were the big thing. I think you guys still know who Michael Jordan is. I hope. And if someone says, you mean like LeBron? No, get out. Absolutely not. No, do not bring up LeBron James and Michael Jordan in the same sentence. Don't. Just don't. Okay. So what we're talking about here is all of your crystals come in what's called unit cells. Now, I'm not actually going to make you learn all these unit cells. I just want you to know they exist. So you can see the relationships between the size of the unit cells and their various angles. These are all going to be definitive of the crystal that you're looking at. So, like for example, the hexagonal unit cell. There is a crystal that's very well known that has that unit cell because its macro structure looks just like the unit cell. What's a popular hexagonal crystal? I have no idea. Now I want to know. No, quartz. Stop throwing things at me that I didn't prepare for. Okay. So quartz, if you look at a large quartz crystal, it has that hexagonal shape. So again, you can see the unit cell dictating that on larger and larger levels. The unit cell, of course, is going to be your smallest repeating unit. So crystals, what they're going to do is they're essentially going to just cut and paste this unit cell over and over and over and over again, and you get your long range symmetry. So the way we analyze crystals is through X-ray diffraction. You get your so a couple fun things you can do in graduate school. First off, there's solid state chemistry labs where you're going to grow crystals. You get to play with the funnest machines because they're these little machines that you actually get to make lava in. Because you have to melt the whole thing down. And there's a couple of ways to grow a crystal. Like for example, you can get a look like a little ice pick looking thing. You have what's called a starter crystal on the end of it. Because when you dip it in the molten fluid, the molecules and atoms in there are going to start to mimic the parent crystal. And it will grow and grow and grow and grow. And as you pull it out, you pull out a crystal. And then you have to cry because you crush it into powder and then you put it under an X-ray diffraction machine and try to figure out the structure. So, one thing that has to happen is for you to get a reading, you learn the structure by both getting readings and non-readings. So the readings come when the X-rays going in experience a lattice that is a whole number multiple of the wavelength of the X-ray photon. This ends up leading us to what we know as Bragg's law. So there on the right, you see that's an actual X-ray pattern from the crystal. You can start to see the locations of the planes, the atoms. And so what you're going to get is light waves are going to go in. Light waves that hit the first plane are traveling less distance than light that hits the second plane. Now that extra distance is going to have to make up that whole number multiple of the wavelength to get a bright spot. Otherwise, you're going to start to get dark spots. This is called constructive and destructive interference. For constructive interference, waves have to be phased. For perfect destructive interference, you have antiphasic. Can anyone tell me what phasic means? It's the same thing that happens in a laser. The photons go into usually like a partially silvered glass chamber. They can't escape the chamber until they achieve a certain energy. Where they stay in there bumping into each other until they all achieve, they become phasic. Then they have enough energy to stay. You what? It is, but you tell me what that means. Base speed, if all of that lines up, you know what else lines up? The amplitude, the weights themselves are going to line up perfectly. So phasic means peak, trough, trough. So that's phasic. So remember Bragg's law here. You're in this case, n is your whole number multiple. Be 1, 2, 3, whatever. And then 2d sine of theta, we're going to figure that out. So if you look here, you can see constructive versus destructive. This is what we mean by phasing. The one on the left is phasing. You know, they all line up, and then when those two waves interact, you're getting stronger waves. Versus the one on the right, which is anti-phasic, it's a perfect, what we call 180-degree phase shift. And so the one on the right, the phasic will be 0-degree phase shift. The waves line up. Now, if you do 180 degrees of phase shift, you end up with waves where peak meets trough, and they interact, we call interfere destructively. So then the waves will essentially cancel each other out. Now let's start talking about why Bragg's law is what it is. So we talked about these waves having to exit the crystal as a whole number multiple of the wavelength to remain phasic. Now let's talk about these extra path lengths. The light going into the bottom has to travel an extra distance, and it has to meet that whole number multiple of the wavelength condition. So what are those path lengths that it has to travel? Well, as the wave on the top reflects, the wave going into the bottom has to go an extra CB plus BD. So those are those individual lines that you can see there. That's your additional path length. Now, can we prove that that is a whole number multiple of the wavelength of the radiation? Well, do you see the triangles there? Yeah. So anyone who ever takes my physics class, the more creative you can draw right triangles, the better off you're going to be. The triangle 1, triangle 2. So let's take a look at that first triangle. Again, Bruss told me this was funny. So, also, I want to know if anyone could ever solve the ancient philosophical question, are zebras black with white stripes or white with black stripes? I'm still waiting for an answer. I don't know, you ever shave a tiger? Its skin has the stripes. So it's hard to, it's hard to tell.
Women have stripes on their body, more cats can see.
That sounds like a conspiracy theory.
Like the XX chromosome.
That sounds like a conspiracy theory. Well, but that's how, I mean, that's how nature works. Like, tell me what sounds more ridiculous. A horse with a horn or a leopard moose camel with a 40-foot neck? We have one, we don't have the other. So let's look at these triangles. So our first one, that's a heck of a party question. Do you have stripes? So these are right triangles. The thing that always happened to me at parties is people would have to find me. It's like, they'd be like, why are you on the roof? And I'd be like, there was a ladder. I'm like, that's not a reason. That's not. So look at this. Now we know that we have line CB. And then this center line is D, the spacing between the layers of the crystal. Okay. Who remembers their trig functions? Yeah, so which one am I going to use here to relate line CB to side D? So line CB is directly across from theta, which is what? No, not adjacent, opposite over hypotenuse. Nope. So tangent is opposite over adjacent. So we want opposite over hypotenuse. Sine. We'll use the sine function. And if we rearrange, side CB has a length of d sine of theta. Let's look at the next triangle. You're going to be shocked how this one turns out. I can't believe I'm getting like triangles right today. I actually typically draw parallelograms, but accidentally. I'm really good at drawing a 6-dimensional triangle because it looks nothing like a triangle. So here we have line BD. And then again, we have the D, the spacing between the planes. Well, it's the same thing. So it's the opposite. So the sine of theta and so we rearrange this. Now we know that the extra distance has to equal the whole number multiple of lambda in order for constructive interference to occur. So then if we have in lambda, we're going to get d sine of theta plus d sine of theta, or Bragg's law. On Monday, we'll start by solving some exercises with this and kind of get an idea of how this works in experiment. They're fun labs. Get the big electron gun set up, you put your crystal in there,